Welcome to Finding Vertical Asymptotes of Rational Functions. All right, I hope everybody knows what a vertical asymptote is. It's a vertical line that goes up and down that basically the function is not allowed to cross. But let's talk a lot about what specifically they are and how to find them in rational functions. So first, how to identify vertical asymptotes. If the value a is a real zero of the polynomial in the denominator of a rational function and is not also a real zero of the polynomial in the numerator, then the graph of the rational function has a vertical asymptote at x equals a. Let me repeat that very clearly. If a value, x equals a, only makes the denominator equal to 0, there will be a vertical asymptote at x equals a. If it makes both the numerator and the denominator equal to 0, that is not a vertical asymptote. Now let's talk a little bit more about how a vertical asymptote is a new type of discontinuity. We've seen holes before in graphs, and we've talked about jumps that could be discontinuities, but a vertical asymptote is a brand new type of discontinuity. So a vertical asymptote at x equal a is a disruption in a graph and therefore creates a value where the graph is not continuous. So here are some signs that you have a vertical discontinuity. One, there is no value at f equals a, or at f of a. So if you try to plug a into the function, you don't get anything out, DNE. And the limit as x approaches a is it does not exist. So these are two signs you're working with a vertical asymptote, but there's also a couple of things that have to happen, but this is really specifically where we'll see this disruption in the graph. Now, near a vertical asymptote, x equals a, of a rational function, the values of the polynomial in the denominator are arbitrarily close to 0. So the values of the rational function increase or decrease without bound. All right, this is a little bit confusing, so let me explain. Remember, we're working with rational functions here, where we have a numerator function, or a numerator polynomial, and a denominator polynomial. Now, remember, vertical asymptotes occur at a value that makes only the denominator equal to 0. But what about if we talk about as we get close to this value? So let's just say that x equals 2 only makes the denominator equal to 0. Now what happens if we get really, really, really close to 2? Now this is what we call a limit, right? Getting close, not equal to 2, getting close. So we're talking about getting close from the left side, which would be 1.9999, 1.999999, 1.9999. So if we get super close to 2 from the left, or we could get super close to 2 from the right, like 2.001, 2.00001, 2.000000001. So we're getting really, really close from both sides. Now, remember, 2 makes the denominator equal to 0. But if we allow it to get really close, if we allow x to get really close to 2, well, then that means the denominator is going to get really, really close to 0, but not equal to 0. 2 makes it equal to 0. 1.99999 or 2.00001 will make the denominator not equal to 0, but really, really close to 0. Now, what happens if you take a value in the numerator and you divide by a value in the denominator that's super close to 0? Well, get out a calculator and try if you want. Like take 5 divided by 0.0000001, something really, really, really close to 0. Well, you don't get closer to 0. You don't get, what happens is you get really, really big or really, really small. You get towards positive or you get towards negative infinity. So again, try it out if you don't believe me, right? So if we have a numerator not equal to 0, and we divide by a number really close to 0, okay, I want to emphasize the vertical asymptote turns the denominator into 0. That's a DNE, does not exist. But as we get close to 2, the denominator is going to get close to 0, like 0.0001 or 0.0000001. So as those values get closer and closer to 0 in the denominator, and the numerator stays a value, for example, 5, you're exploding either towards infinity, or maybe if that was a negative 5, towards negative infinity. You're going to get really, really big or really, really small. So this is another sign that we're working with a vertical asymptote. If you identify or if you analyze the limit as x approaches the vertical asymptote A from the left or the right. Now let me emphasize this because this might be new. So if we put a little plus sign right here or right here, we're talking about approaching from the left or the right. So if we say X approaching A, and we put a little minus sign there on the upper right-hand side, that means we're talking about specifically approaching from the left. A little plus sign means we're specifically approaching from the right. Okay? So again, if we're talking about approaching 2, and we want to approach 2 from the right, we're talking about the right side of 2, 2.0001, 2.00001. And if we're talking about approaching 2 from the left, we're talking about coming at 2 from the left side, which would be 1.9, 1.999, 1.99999. So the point is, as we approach a vertical asymptote from the left and from the right, well, we're not allowed to cross that vertical asymptote because the vertical asymptote is where the denominator equals 0, and that can't happen. So the function's either going to go straight up towards infinity or straight down towards negative infinity, because those are its only options when you're approaching a vertical asymptote. But again, I want to make sure you understand why this is happening, why the function's going towards infinity or negative infinity, and that is because if the denominator is getting closer and closer and closer to 0, when you divide, because that's what denominator does, you're dividing by it, when you divide by a number closer and closer and closer to 0, the overall fraction actually gets super, super big, either big in the positive direction or big in the negative direction. Let's just take a look at an example so you can actually see more specifically what we're talking about here. So here's a function x plus 2 times x minus 3 in the numerator and x plus 1 in the denominator. Now it's pretty clear what value makes the denominator equal to 0. That would be x equals negative 1. So that is a vertical asymptote. It does not make the numerator 0. Again, vertical asymptotes specifically only make the denominator equal to 0. If you make both the numerator and the denominator equal to 0, that's something special we're going to see in another video. But notice what's happening here at negative 1. Now you can obviously look at the graph. First off, we do see that blue vertical asymptote at x equals negative 1. Not allowed to cross that vertical asymptote. So if we try to plug negative 1 into the function, let's go ahead and do that. If we plug negative 1 into the function, on top we're going to get 1 times negative 4. 1 times negative 4 is negative 4. But when you plug negative 1 into the denominator, you're going to get a 0, hence dne. And then now take a look at the graph. If we think about the limit as we approach negative 1, remember we've talked about limits in the past, we have to think about approaching from both sides, and for a limit to exist, the left side and the right side have to be coming together at the same value. Well, just looking at this graph, the left side of our function is going towards infinity. The right side of our function is going towards negative infinity. The two sides are certainly not coming together, which is why the limit does not exist. But because we now can analyze the limit from the right side or the left side only, we can now be a little bit more specific in terms of what's actually happening here. So as we approach negative 1 from the right-hand side, so as we get closer and closer and closer to negative 1, if we're following our function from the right-hand side, what's happening is the function is going down, 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 down. Because if I plug a number super close to negative 1 in from the right, then with the denominator is actually going to be super close to 0, but not equal to 0, but really close to 0. And when you divide by a number really close to 0, you're going to become super, super big, either big in the positive direction or big in the negative direction. So it turns out from the right-hand side, we're going super big in the negative direction. And then approaching negative 1 from the left, so again, following the function as we approach negative 1 from the left side, we see that the function is going up, 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 up towards positive infinity. So although the overall limit does not exist because the two sides do not come together, if we do specifically analyze each side of the function, that's what the little plus sign, minus sign is for, we do see that one side is going down towards negative infinity and one side is going up towards positive infinity. And again, that's what's creating this vertical asymptote. So although a vertical asymptote is very easy to explain and show, it's a vertical line you don't cross, there's really a lot of details into specifically what's happening as we approach that value, which is why analyzing the limits as you approach a vertical asymptote are super important to understand. All right, so let's look at another problem here, and again the goal is to find vertical asymptotes. So again, very easy to find vertical asymptotes. I'm not trying to make that hard. It's simply values that make the denominator equal to 0. So if I say, okay, what value makes this factor equal to 0? That's actually pretty easy to do some mental math there. -4. What value makes this factor equal to 0? Well, add the 3, divide by 2, and we get 3/2, right? All you have to do is take the denominators, factors, set them equal to 0, and determine what values make them equal to 0. And we get -4 and 3/2. Now, it's really important that they don't also make the numerator equal to 0. So what values make the numerator 0? Well, -2 is going to make the numerator 0, and 1/3, add the 1 divided by 3. No, those are zeros. Those are zeros. Different video, we talked about that already. Those are zeros. They only make the numerator equal to 0. But again, vertical asymptotes, use VA for short there, vertical asymptotes, are numbers that only make the denominator 0, and that would be x equals -4 and x equals 3/2. So first off, this tells us a lot of information. First, we're going to have discontinuities. The graph is not continuous at vertical asymptotes. So it's a new type of discontinuity. And at these two values, there's nothing, dotted lines, right? Nothing. And then as we approach these values, the limit does not exist. But if we look at one side in particular, we're either going to go up towards infinity or down towards -infinity. So here's an actual graph of this function where we had those vertical asymptotes at x equals -4. And x equals +3/2. So we actually see here's the one at -4, here's the one at 1.5 or 3/2. Remember, the dotted lines are just there for you to see it. Those dotted lines are not actually in the graph. They're imaginary. They're well, not imaginary numbers. They're invisible is a better word, right? Those two dotted lines are invisible. You don't actually see them, but we put them on the graph so that we emphasizes them, right? So if we said to you, okay, what's happening at -4, right? What is the value at -4? Well, dn nothing is happening there. What about the limit as we approach -4? Now, if there's no little plus sign or minus sign, that means from both sides. And one side is going towards infinity and one side is going towards -infinity, so the limit does not exist. But again, if we specifically looked at the left side, we would say infinity. If we specifically looked at the right side of -4, we would say -infinity. But again, they're not coming together to specific numbers, so the limit does not exist. And then likewise, we could also analyze 3/2. If we talked about what happens at 3/2, well, nothing, dne, nothing. You're going to get a 0 in the denominator, and you cannot have a 0 in the denominator. That produces a dne. What about the limit as x approaches 3/2 for this function? Well, that would also be dne. Again, the two sides, left side's going down, right side's going up. They're not coming together, therefore the limit does not exist. But once again, limits with this new little notation. If we do add that little minus or plus sign, we can specifically look at one side of the limit and see that the left side is going towards -infinity, the right side is going towards +infinity. One more time, why are the functions going straight up or straight down? Because if the denominator gets really close to 0, not equal to 0, and that's what numbers near -4 are going to do. Numbers near -4 are going to make the denominator really, really close to 0, and when you divide by numbers that are super close to 0, like 0.00000000001, your overall value is going to be really, really big, or big positive or negative. All right, now let's take a look at this example here. Now this one's unfactored, so sometimes you might have to do a little bit more work here. So we're saying, okay, let's see what values allow for the denominator to be equal to 0. Now it is a quadratic, so you can either factor it or you can use the quadratic formula if you're not sure. But let's go ahead and factor this one. Should be pretty easy. X plus 3 times x minus 2. If you don't believe me, just check that work. X times x is x squared. 3 times -2 is -6. 3x on the inside, -2 on the outside makes the x in the middle. So this means that x equals -3 will turn the denominator into 0, and x equals 2 will turn the denominator into 0. But don't stop there, because remember, if you also turn the numerator into 0, you're not a 0, you're not a vertical asymptote either. So even though I'm emphasizing vertical asymptotes are numbers that turn only the denominator equal to 0, to make sure it's only the denominator, you do actually have to check the numerator as well. So I'm going to go ahead and say, all right, what numbers turn the numerator equal to 0? So I'm going to go ahead and factor this. I believe it's going to be x minus 4 times x plus 3. If you don't believe me, go ahead and check my work. And that means x equals 4 turns the numerator into 0. X equals -3 turns the numerator equal to 0. So I see an issue. Negative 3 is not a vertical asymptote, nor is it a 0, because x equals negative 3 turns both the numerator and the denominator equal to 0. That is going to be something completely different. It's not a 0. It's not a vertical asymptote. We'll talk about that in a different video. So x equals 4 is a 0 because it turns the numerator into 0. X equals 2 is the only vertical asymptote because it turns the denominator only into 0. So here's a look at this graph right here, and we see that x equals 2. We see this beautiful, gorgeous, amazing vertical asymptote. And what happens at 2? D and E, nothing. When you plug 2 in, you get 0 in the denominator, and that's just not allowed. What about the limit as x approaches 2 for this function? Well, the left side's going up forever, the right side's going down forever. That is a D and E. For a limit to exist, the two sides have to come together at the same value. So what happens here is if we did look individually at the left side, we're going towards infinity. The right side, we're going towards negative infinity. But overall, the limit does not exist. And that's what's prompting the vertical asymptote. All right, let's just do a couple more examples here. All right, real quick again. All right, got to figure out what numbers make the denominator equal to 0. That's how you find vertical asymptotes. You can go ahead and factor this one. That's a difference of squares. Everybody should be able to factor this one. And we get two solutions of x equals 3 and x equals negative 3. But don't stop there, because check out the numerator as well. The numerator equals 0 when x equals negative 3. So negative 3 and negative 3 turn the numerator and the denominator equal to 0. So that's not a 0, nor is it a vertical asymptote. So in this case, we only have a vertical asymptote at 3. All right, how about this one over here? Notice it's the same thing, just switched around. So once again, the denominator equals 0 when x equals negative 3. Yay, okay, great. The numerator equals 0 when x equals negative 3 or positive 3. Whoop, that should be a minus right there. Sorry for my messy handwriting. So that's negative 3 or positive 3. So now wait a minute. Negative 3 makes both the numerator and the denominator 0. So that is not a 0, nor is that a vertical asymptote. Now positive 3 makes the numerator 0. So that's a 0. So this graph actually has no vertical asymptotes because there's no value that makes only the denominator equal to 0. Negative 3 does make the denominator equal to 0, but it also makes the numerator equal to 0. So that is not a 0, nor is that a vertical asymptote. So here are the graphs of these two functions. On the left here, we did have one vertical asymptote at x equals 3. We see that beautiful dotted line there that represents the vertical asymptote. At 3, there's nothing, D and E, and the limit as we approach 3 does not exist as well. The left side's going down, the right side's going up. Now in this graph over here, remember we conclude that there was no vertical asymptote. So look at that beautiful graph. No vertical asymptote whatsoever. So be careful. You have to check the numerator and the denominator. All right, now there's one more kind of rule here. It's a little bit funky, but I want to make sure I explain it very clearly. Okay, so an amendment to our definition of vertical asymptote. So furthermore, a vertical asymptote also occurs at x equals a if the multiplicity of a has a real 0 in the numerator is greater than its multiplicity as a 0 in the numerator. So here's an example where we see x minus 6 in both the numerator and the denominator. Okay, so if we said, hey, what's going on with 6? Well, we say, wait a minute, 6 makes both the numerator and the denominator equal to 0. So, if you've been listening to everything I've said so far, you would just say, well, I guess this graph has no vertical asymptote because 6 makes both the numerator and the denominator equal to 0. So that's not a vertical asymptote, nor is that a 0. Well, we're making an amendment to that. That's because these are repeated factors, right? On top, we have x minus 6 times x minus 6. And in the bottom, we have x minus 6 times x minus 6 times x minus 6 times x minus 6 times x minus 6. I'm not going to write it out 5 times. But if you think about what's happening here, this function would actually reduce. Because if you have a common base, you could subtract the powers, or you could think about them canceling or reducing out, right? The x minus 6, the 2 of them in the numerator are going to cancel out with 2 of them from the denominator. That's going to leave behind a 1 in the numerator and an x minus 6 cubed in the denominator. Okay, let me actually write them all out here. So we got x minus 6 times x minus 6 times x minus 6. That's 3 of them times a fourth and times 1 more. I'll squeeze it in there. So what's going to happen is these two are going to reduce to a 1. These two common factors are going to reduce to a 1. So that's why there's a 1 left in the numerator and an x minus 6 cubed in the denominator. So if we look at the function like this now, where the multiplicity was greater in the denominator, multiplicity was 5 in the denominator versus 2 in the numerator, this is where you would have a vertical asymptote at x equals 6. Because now that you clean it up and simplify it, you see that x equals 6 does only make the denominator equal to 0. So that's the only time we could have an amendment to that rule about if you make both the numerator and the denominator equal to 0, you're not a vertical asymptote. If it deals with multiplicity, and all the examples we've done so far before, the multiplicities were all 1. So here, if the multiplicity of the value is greater in the denominator, that will produce a vertical asymptote. So really it's just simple, right? Just simplify it and you'll see it more clearly. Oh yeah, 6 only makes the denominator equal to 0. Therefore we have a beautiful, wonderful vertical asymptote at x equals 6. All right, hopefully that video or this video makes sense for exploring vertical asymptotes, understanding how to find them, which I think is pretty easy, but also understanding what they mean graphically and using limits, how to make sense of what's going on at those vertical asymptotes.